All right, let's talk about how to construct an exponential growth model. We're going to start with a skeleton here, and I'm going to call it capital A, as in the amount of something that I have at a given time t. So the amount of something at a given time t is going to be equal to C E lowercase a t. You know, I don't like C. I don't like C. Let's trade C for A0 or A sub 0. A sub 0 is the amount of whatever the thing is that I'm talking about that I have at the very beginning. So you'll see in these equations like, oh, t equal to 0, that's the amount that you have when t is equal to 0. This here is the skeleton of your exponential growth model, as in the amount of something that you have at a given time is equal to the amount that you had at the beginning times the natural exponent raised to some rate lowercase a, and some time t. Let's go through two examples of how this skeleton form can be used in, let's say, a word problem. So I'm going to use a different color. I'll go to black. First word problem. Let's see. Oh, okay. So let's say in the year 1960, the population of a given country was 25,000. And in 1970, the population has grown to 30,000. We want to know, what could we expect the population to be in the year 2000? This is population. This is year. So let's take this information and correlate it into our skeleton that we have. So A of t, the amount that I have of a certain thing at a certain time, is equal to the amount that I initially had times the natural exponent raised to some rate times the time interval that I'm interested in. Okay, so the initial year here, the initial one is going to be 1960, which means the amount that I had at the beginning is 25,000. So we'll say it's going to be equal to, that's going to be 25,000 times e to the a. And as far as t is concerned, t is going to have to be 10 years, because I went from 1960 to 1970. So that t is going to have to be 10 years. And that means that the amount of the thing that I'm interested in, which is my population, is going to be the amount that I have at 10 years. And the amount that I have at 10 years is 30,000. So my skeleton equation, which was the amount of something that I have at a given time is equal to the amount that I had at the beginning times the natural exponent raised to the rate times the time interval. So the amount that I have at a given time is 30,000, and I have that in 1970, is equal to the amount that I had at the beginning, which was in 1960, I had 25,000, raised to the natural exponent of some rate adjustment constant A times the time interval, which was 10 years from 1960 to 1970. So our skeleton equation has just turned into something that only has one variable to solve for. So how are we going to do that? Well, we need to isolate. So it's going to be E, the 10A, equal to, we're going to have to divide here. It's going to be, we'll get rid of some of the zeros. We'll say 30 over 25. Well, which is equal to 6 over 5. So we'll just swap that out, 6 over 5. Okay, so now we need to get this 10a out of exponential world and bring it back to solvable world. So we're going to take the logarithm or the natural log of both sides. When I do that, when you take the natural log of e to the anything, you just get the anything, and the other side is going to be the natural logarithm of 6 over 5. So it's going to be 10a equal to ln 6 over 5. All right, let's grab our trusty calculator here, and we'll say ln of 6 divided by 5. I'll go 4 decimal places on this. 10a equal to 0.1823. And now we're going to solve for a. So we're just going to divide both of them by 10. And a is equal to 0.0182. Lowercase a was that rate constant, that exponential rate constant. So we know now that the exponential rate constant is 0.0182. That's all good. We've got a working equation here and everything, but the question asked us, what's the population going to be in 2000? So from 1960 to 2000, that's going to be 40 years. So let's just go back to using our skeleton as it was. I'll throw this second part of the question in another color, and we'll go to light blue here. Skeleton equation. The amount of something that I have at a given time is equal to the amount that I had at the beginning times the natural exponent raised to the rate constant times the time interval. The amount that I have at a certain time that I'm interested in is what happens in the year 2000, which is 40 years. So it's going to be a of 40 equal to the amount that I had at the beginning, which was 25,000, times e to the at. Well, t is 40 and a is 0.0182. Let's just do that multiplication real quick to make our lives a little easier. 0.0182 times 40. 0.728. So this is going to be raised to e to the 0.728. Well, now that's very manageable at this point. So it's going to be a of 40. What's the amount that I have in 40 years, given what I initially had here, is going to be 25,000 times e to the 0.728. So that's going to be e to the 0.728, 2.0709, 2.0709, 2.0709 times 25K. $2.0709 times 25,000, 51,772.5. So how do we conclude? We say, based on the data given to us, with an initial population in 1960 of 25,000, and an increase over the next 10 years to 30,000, we can predict that the 40-year difference is going to yield a population of 51,772 and a half people. Maybe if we wait just like another few days, we'll get to 773. But that's how we use our skeleton to solve an exponential growth problem. So let's try another one. I'll keep the skeleton there, as we'll use it again. Let's say there was a petri dish full of little bacteria. And we were told that in 10 hours, the number of bacteria is going to increase by a factor of 6x, meaning that when time is equal to 0, we're going to have, I don't know, let's say X number of bacteria. And then at time equals 10 hours, we're going to have 6x, that amount of bacteria. But what we want to know is how long will it take for the initial amount of bacteria to double, meaning 2x? And we're told that in 10 hours, it'll multiply by 6x. You think, oh, 6x in 10 hours, 2x might be like, I don't know, 3 1/3 or something. That intuition is not appropriate for using these growth models. Let's do it by the numbers here, okay? We'll use our model. We know that the amount that we have at a certain time is equal to the amount that we had at the initial time times e raised to the rate change times the time. So the amount that we have at a given time, we're not told exactly how many bacteria there are, but we are told that there are 6 times as many of them in 10 hours. So we can say the amount of bacteria B0 equal to B0 e to the a times 10 hours. And then I'm just going to slap a 6 over here. Because now I said the amount that I have right now is equal to the amount that I had at the beginning times e raised to the a times the time. And the amount that I have right now is 6 times what it used to be. So let's just be easy on ourselves here. Those can go away. We're going to be left with 6 equal to e to the 10a. We're going to use a similar trick as we did before. We can just but take the natural logarithm of both of these, and whatever e is raised to, we'll be left with that as itself, and we'll just keep the ln of 6 over here. So it's going to be ln of 6 equal to 10a, which tells us that a is equal to natural logarithm of 6 divided by 10. Grab a calculator, do that one up real quick. We're going to have ln of 6 divided by 10, which is going to be 0.17918. As I was. That's going to be 0.1792. So now we know what the rate change constant is over the course of this time. So how long for it to double? So now we need to solve for time. We need to know how long it took for it to double. So I'm just going to move this over here for a second, and I'm going to say A equal to 0.1792 92. That's what we just solved for. I'm just gonna make myself some room here. How long for it to double? Well, 10 hours, 6x, an unknown number of hours for 2x. So again, I'm gonna say amount of bacteria is equal to amount of bacteria at the beginning times e to the AT, but we know A, and it's gonna be 0.1792 T. And the amount that I'm curious about is double the amount. So now the unknown variable in here is the time. So let's do as we did before. Goodbye to the B's. We're gonna have 2 equal to e to the 0.1792 T. Same trick as before. We're gonna take the natural log of both. It's gonna leave us ln 2 equal to 0.1792 T. And now we'll just divide both sides by 0.1792, leaving us with 3.868 hours. How do we conclude? We say, based on the data that we were given, we were told there was a petri dish with a certain amount of bacteria in it, and that in 10 hours, that amount of bacteria increased by a factor of 6x. But what we were curious about was how long did it take for it to double? So to get from 2x, something like that here. We solved our skeleton equation for the rate change constant A, and then we readapted this skeleton equation to solve for double the initial, and that told us that the bacteria doubled in 3.868 hours.